I'm Erik Ringdahl. I am the product director at foreseeti, and I'm going to talk about automated threat modeling and attack simulations in the energy sector today. I'm going to start off briefly, just talk about cybersecurity in general in the energy sector, a lot of the things that Robert already talked about, and then move into threat modeling and attack simulation in critical infrastructure and how that typically works. And how we can use that to do non-intrusive attack simulations and automated threat modeling in organizations and systems like this. We're going to talk about the concepts behind it, and then we're going to look at some cases, some example models. One smart grid network, the one that Robert mentioned earlier, and if we have the time, we will also look at how we can design a new data center for critical infrastructure. So the increase of automation is causing a lot of issues in the cybersecurity postures for utilities and the energy sector, and a lot of the issues are what Robert mentioned. So the complexity and bringing in a lot of IoT devices and off-the-shelf software, and threats to these systems generally arise from, of course, malicious actors. It can be your state-sponsored attacker or your opportunist and a cyber criminal, but also, of course, in combination with software vulnerabilities, poor system design and implementation, and of course, configuration mistakes, for example. And all of these things together makes the systems really vulnerable. And there are, of course, a lot of examples of breaches in recent time, and it really makes it urgent to understand the feasibility and the imminence of these potential threats ahead of any major catastrophe that can happen to these energy systems. If you have a nuclear meltdown or your whole city is shut down because the energy system is hacked. And these systems also present some unique challenges because you have to ensure availability and reliability at all times because you are providing such an important service. But there's also the issue of safety. So if a nuclear site is hacked, for example, or it can cause a lot of harm to a society. And one key thing is that, I mean, you can't protect what you don't know. So if you don't know your system at all and all the intricacies of it, of course, you can't defend it in any good sense. But just knowing everything that you have and how it works is not actually sufficient either, because you don't understand how all of these things affect each other. And large interconnected systems are really hard to grasp as a human. As you saw in Robert's presentation, I mean, just a single application like a browser has so many dependencies to internal systems and code, but also to external things, and it's really hard to really understand how all of this works together. And some, I mean, traditional attack simulations and also pen testing you can use, of course, to get a better grip of how an attack might propagate through your environment. But of course, this might also affect your availability. So if you let the pen tester loose in your energy system, you might lose the power plant or the energy system because the pen tester is actually breaking something. And it's also typically very limited in the scope. So you don't get the full picture of all of this complexity, and also biased, of course, towards the pen tester itself. And all of this, the complexity is the big enemy here. And there are a few options. So threat modeling is a great methodology to help you understand and lessen the noise of complex systems and how an attacker might behave in your system. But this is really traditionally a very manually and time-consuming process, and it's not suitable at all for large complex system because the workload is just too much, and as systems change more and more and rapidly, it's just not feasible to keep track of everything in your threat models. With securiCAD, we can actually run non-intrusive attack simulations and automate this threat modeling process for you. And we can use this to then predict how an attack might propagate through your infrastructure, from the internet, for example, to your SCADA systems or your critical processes. And we can also use this to analyze the causes and effects of different types of threats and attack scenarios. If you have an insider, for example, a compromised software vendor, or a state-sponsored attacker coming from the internet. And we can also quantify the impact and the probability of you actually being compromised, and with this also suggest mitigations of what to fix first and why. And securiCAD is also non-intrusive, as I mentioned, so it will never affect your actual system like traditional attack simulations or your pen tester might do. And it requires no agents or any security expertise really to actually run this simulation. And the high level concept is that we generate the model or build a model manually, if you like, of your system. We then simulate attacks on that model to then be able to find, prioritize, and mitigate any weaknesses or mistakes that you have made in your design, for example. So these models then, or digital twin, if you like, can be generated automatically based on data that you have, or you can build a system or a model of your system manually, for example, in the design phase of a new infrastructure. And these can also be mixed and matched, so you can enrich your manually created model with data, for example, from a vulnerability scanner or a firewall configuration. And really, we can generate models from anything that describes your environment in any way. So your CMs, your asset inventories, your Active Directories, or anything like that somehow describes any part of your system, or any vulnerabilities that might be there. We can then use these models to automatically generate threat models or attack graphs based on this. So all of the logic and the attacks that the attacker will do in our simulations are actually built into these models. So you don't need any security expertise. You just need to know your domain and your systems. And this methodology is a subfield of artificial intelligence called reasoning with uncertainty. And basically what we do is we have a statistical model or a probabilistic inference that we do with Monte Carlo simulations. So we sample the probabilities of an attacker succeeding with certain types of attacks and attack steps in this model. And we can then calculate the shortest path through the model. So from the attacker's entry point then to your high value asset. And with this statistical method, we can also quantify the actual risk of a successful attack on your system. And the metric that we used is called time to compromise, or TTC. And it's the probability over time that an attacker will actually succeed to compromise your high value assets, whether it's your substation or your office environment or your SCADA systems or whatever it might be. And then based on these simulations, securiCAD will then generate a report on your risk exposure, any threats or weaknesses that you have in your model, and also critical attack paths. So with these shortest path calculations that we do after the Monte Carlo simulations, we get the shortest path from the attacker's entry point to your high value assets. And what these critical paths will do is actually expose any top threats or weaknesses or misconfigurations that the attacker will exploit to reach your high value assets as soon as possible. So what is the easiest and the path of least resistant for the attacker in our simulations. And based on these critical paths, the tool will also suggest mitigations. So what should you fix first to stop the attacker as soon as possible and lower the risk exposure as much as possible as well. And all of the logic of the simulations and models are built or defined in a framework called the Metatag language. And I think Simon Hacks will talk more about this later. So I will just mention it briefly. But this is a framework where you can actually formalize the laws of your domain and the simulations. So you can specify all the assets, whether it's your RTU or PLC or an actual office worker, for example, browsing the web. So all of that logic is defined in this framework. So you can specify your assets and also the attack steps and also defenses, so things that can stop certain attack steps. For example, multi-factor authentication will stop an attacker from using a stolen password to access an account, for example. And here we can also define probabilities. So what is the likelihood of an attacker succeeding with this type of attack? And it can be based on information that you have about your system, but also typically it's based on research that Robert mentioned earlier. So studies on how likely it is that, for example, a user will not be able to identify a phished website or things like that. And all of this is built into this specification, so you don't have to use the tool. You don't have to have this expertise because it's all built in to the model and to the simulations. And this makes it domain agnostic as well, so you can define anything, as I mentioned, all the way from your PLC up to your cloud environments and users and soft values such as your security awareness or and policies and things like that as well. There are some typical use cases for this. We're going to look at two of them today. So the first one, the proactive modeling at design stage, as also Robert mentioned, that when you're building something new, you want to build in security from the start. So you can build a model of something that doesn't exist yet, and you can run simulations on that and analyze your model and compare different designs to each other. And of course, you can also model something that exists, also manually if you like, or you can import data to generate the model of your existing environment and get reports on your security posture that you have now, or any return on investment on new security controls or changes to environment. Since the simulations are quantified, you get a quantitative measure of how good your design is or your actual system is, and what changes, how the changes will affect your security posture versus the money it costs to actually implement them. And we're going to look at both of them today if we have the time. So the first one is the first demo case that I have is analyzing a smart grid network, which Robert mentioned. We're going to look at the resilience of the distribution system operator and specifically the SCADA systems in their domain. And the attack scenario that we're looking at is a phishing email and also the exploit of any public-facing applications and how that might affect our security. And if we have the time, we're going to look at how we can design a new data center for critical infrastructure. And also in this case, we're going to analyze the implications of shared hardware between users of these of this data center. And there, the attacker will start with one of the customer sites being compromised. So the first one, the smart grid network, is an example model of a smart grid network, and it's available at community.securiCAD.com, so you can download this model and look at it in securiCAD yourself. And it's based on the EU project as well called CGRID. And so we're going to jump into securiCAD now and take a look at our model of the smart grid network. So we can open the model here in the modeling tool. And you might recognize the layout here of the smart grid network. So we have our hardware and software vendor here. We have our TSO, the data hub, the energy supplier office, and we have a network topology of our DSO, the SCADA systems, and so on. And we have the substations here at the bottom. And we can also take a look at another view of our model. So this is the SCADA zone. We have our SCADA network, your typical SCADA servers, historians, file transfer server here, some data engineering interfaces, the SCADA interface, domain controller, and so on. And we have our process zone here as well. And we can also take a look at some of the data flows. So we have our attack scenario here at the top. Our attacker is on some hacked box and is here sending phishing emails, both to the mail server and to one of the office computers. And we can follow the data flows. So how is the office computers and mail servers communicating with the SCADA zone? So there are some data flows here going through the enterprise firewall and the DMZ, down to the SCADA HMI, and down to the SCADA server, which is talking to the front end, which is going down to one of the substations here. So this is one of the data flows through our environment. And yeah, the attack scenario is the attacker is sending emails, and our high value assets are the servers in the SCADA zone. So we have the SCADA server here, and also some process data here. The yellow ones are the objects that we have selected as high value assets, but you can select anything that you want to pick as a high value asset, or as many as you like. But in this scenario, we are looking at specifically the SCADA zone, and we are worried that the attacker might reach those assets. So we can take a look at, go back and take a look at the report and the first simulation here. So as I mentioned, we are running Monte Carlo simulation, so we can quantify the actual risk of the attacker reaching our high value assets. So we get a high level report here at the top. Our total risk exposure is almost 100%. So the attacker is reaching all of our high value assets with 100%, almost 100% success rate. And our SCADA historian is reached within 7 days. And we can take a look at our 5 high value assets here. So we have the SCADA server, and we have the front end server, and some data stores here with process data, for example. And for the high value assets, we can get a more detailed look. So we get the time to compromise graph. So this is, as I mentioned earlier, the success rate over time that an attacker will succeeding in compromising, in this case, the SCADA server. We can actually take a look at the critical path for this high value asset and get the path from the attacker's entry point here at the end to our high value asset, in this case, which is the SCADA server. So here we can follow the steps of the attacker and what weaknesses or threats the attacker is using to actually reach our SCADA server in this case. And here we can find not only the top threats, but also possible mitigations that we can apply. And this is the most likely path, but it's not the only successful one. So we can increase the detail level here and actually get other paths that are still possible, but much less likely. For example, the attacker might develop a zero day as a last resort, but that is not the most likely path in our case. So based on the critical paths to all of our high value assets, we can also generate something that we call choke points. So these are the points in our architecture where the attacks converge. Basically, where are our weak spots or spots where we should focus our efforts. So on On the left here is our attacker, on the right are our 5 high value assets. And these are all objects in the model where the attacks converge and points where we can focus our efforts. And we also get a report on our risk, both our overall risk, but also our exposure in confidentiality, integrity, and availability. And based on this, we also get suggested mitigations, or what are the top weaknesses or threats that attacker has exploited that we can actually fix directly in the model. So for example, here we can see that the attacker is exploiting the fact or using the fact that we are using unencrypted protocols in some of our systems. But it might be the case, especially in like OT and SCADA systems, that some protocols can't be encrypted, or they are so old that you don't want to make those kinds of changes. So we will skip that. The same with anti-malware. It might not be possible to do it on SCADA servers, or you don't want to have it on critical systems. But for example, here we get a warning that we are using default passwords, and this is a setting in the model that is set. So we are not prohibiting the use of default password in our models. So for example, the logging into the domain controller, database access, and remote access, we are allowing default passwords on these access controls. The same with some back-off techniques and passport policies. And also another important thing is multi-factor authentication, of course. So both our operators, our admins, and office computers are not using multi-factor authentication, and the attacker is exploiting that fact and can, for example, guess the password because we are using default passwords as well. So these mitigations can actually be applied directly to the model, and we can see what type of return on investment we might get by applying these mitigations to our model. So we can select the ones we want, and we can apply them directly to the model and see how that affects our risk exposure. So for this particular scenario, I have done 4 simulations. So this is our initial simulations where our risk exposure was almost 100%. And we applied some of the mitigations that the tool suggested. So for example, multi-factor authentication to some critical access controls and user accounts. And we also prohibit the use of default passwords here. We also patched our mail server and made sure that no malicious emails could compromise that mail server. And as a last mitigation, we also encrypted our some of our data at rest. So if you remember, we had a few high value assets as data stores, for example, the process data. So we don't want the attacker to tamper with the process data. So that could be encrypted in this example. So these are mitigations that the tool suggests, but you can also apply your own. And if you have rolling out a patch policy, for example, or you want to train your users to be security aware, you can apply those mitigations yourself. You don't have to use the ones that the tool suggests. And you can see what type of return on investment you get from your mitigations. Going back to our examples, we have another case here where we are looking at a new design of a data center for critical infrastructure. And this is actually, it's a new model, but we have imported our smart grid network model into this, and we are designing a data center for customers to access the data from the DSO, basically. So this is just a simple picture of the setup. So we have 2 different customers here accessing our data center, and they have their own VMs in our data center that they can access to get a hold of some business intelligence from the SCADA systems here. So there is connection to the DSO. And the thing we want to look at here is if it's okay to have shared hardware in our data center. So we have our customers here on a hypervisor, but we also have a second design that we want to look at where we don't share hardware between customers in a data center. Of course, that is more expensive, but we want to see if it's worth the investment to actually have separate hardware for our customer instances. And the attack scenario that we are looking at here is that the attacker has actually compromised one of the customer instances, and we want to see if by that attacker can reach the other customer instances or actually reach the production systems in the DSO. So we can go back to securiCAD here and take a look at the data center models. So let's open up this one. So we have our customer 2 here where the attacker is attached, and we, as I mentioned, we assume that this is already compromised. We have our customer 1 site and their respective VMs here, and the gray box here is the hypervisor that the VMs are running on. And here we also have our DSO, so we have imported our smart grid network model and connected it here. So the data center is fetching data from the DSO to get some business intelligence, for example. And we also have our substations here. And we can just take a look at the other design as well. And as you can see here, we don't have the hypervisor anymore. So we don't have shared hardware in this case, and we want to compare these two different scenarios and see if it's worth the investment to have separate hardware, basically. So we can go back to our project, and we have started 2 simulations here with our two different data center models, and just on a glance here, we can see that the risk is almost halved by separating the hardware. And we can go into compare here and get another overview of the 2 different scenarios. So we have our shared hardware here, and the production system is compromised within 162 days. And there's a 50% probability that the attacker will succeed. That might be fine in our case, but the customer 1 VM is also compromised. It's a fairly long time to compromise, but with these types of systems, I mean, you have an expected lifetime of the systems of I don't know, 10, 20, 30 years. So 162 days or 93 days might be critical in this case. And we have the other scenario here where the other customer is not reached at all, actually.